All right, hello everyone. Welcome to my channel. I'm Thomas, and on this channel we do educational matters of mostly the esoteric and obscure variety. And today is the 123rd video that we're doing on the reciprocal system of theory. And this is a theory that almost nobody has ever heard of, but it is a theory of everything that was devised by Dewey B. Larson back in the 20th century. He died back in 1990, having written 15 or so books and dozens of articles on his reciprocal system. Now, the reciprocal system is important to me because it gives you an overview of, it's a theoretical universe. You can plug the system into any subject that you want, as long as you understand the theory well enough to kind of plug it in, and then you, through a process of deduction, if this then that, if this then that, you can really figure out anything. And as a result, you do not have to rely on the experts in the white lab coats to tell you what these things mean. Now, the basic idea of the reciprocal system is that we live in a universe of motion. Not a universe of matter and not a universe of energy, but a universe of motion. And motion is the relationship between space and time. Space and time are reciprocals of each other. Basically, you invert one to get the other. But they don't really exist separately. They only exist together in motion. So motion is a fraction with a time denominator and a space numerator, or vice versa. And all matter, energy, and all other forms of scientific phenomena are strictly and uniquely defined in terms of space and time, because they are all motions. And space and time have the same qualities, one of which is its coordinate nature. Space we know to be 3 or more dimensions, XYZ coordinates, or XY, WXYZ coordinates, or whatever. And therefore, time also has a coordinate aspect. So there's coordinate space and coordinate time. There is also clock time, and therefore there is clock space. Clock time is flowing, it's progressing, it's always getting later and later. Space, too, has a clock aspect. It is flowing, and things are always getting farther and farther apart, which is seen in the Hubble telescope's view of the recession of the distant galaxies. All of the distant galaxies are getting farther and farther apart. The farther away they are, the faster they're getting farther apart. Okay, so that's the basic idea. So Larson started with that, and then he developed his theoretical universe, and then he compared it with the actual universe that the legacy scientists posit through observation and measurement. And really, like 90% of the results of all those measurements and so on over the course of hundreds and thousands of years turned out, in Larson's estimation, to be accurate. There's only those 10% of things that Larson really found the need to correct, and those are generally in the realm of the very fast, the very small, the very large, and the very slow. Things such as atoms and relativistic, or so-called relativistic phenomena, things as large as galaxies and quasars. These are things that the legacy science, pretty much in the same way that Einstein appraised it. The Newtonian laws are accurate but uh, they don't resolve very well at the very margins when they're put under great amounts of stress by huge things or really really small things or really really fast things. Then those relativistic laws start to take control. Larson saw it really the same way. He had a book that was called Beyond Newton. He didn't go from Einstein, he went from Newton. And so also with Einstein, Einstein believed that the speed of light was the maximum speed of the universe. Nothing could go faster than the speed of light. In Larson's system, a universe of motion, motion itself is the background, it is the origin, it is the null point or the neutral point. And so Larson saw the speed of light as the midpoint of the universe. It was the one. So in Larson's system, both time and space are quantized, meaning they only come in chunks. There is no continuity, even though motion itself is a continuity. When you add you can add units of time and space, but they come in small little chunks. It's not like you can't add 0.002 of a unit. It's only one or none. And 1 unit of space in 1 unit of time is the speed of light. Okay, so the speed of light is 1/1. And there is an entire half of the universe that's actually moving faster than the speed of light. Larson calls this the cosmic sector, or sector 2. And then there's the half that we're familiar with that's moving slower than the speed of light, sector 1, or the material sector. Now, right now, we are going over an interview that Larson did back in 1984, when he was an old man, 85 or 86 years old, still had a couple books left in him. And we are kind of in the middle of this interview. He had just got done talking about his kind of epiphany about the idea about a reciprocal relationship that he came upon when he was driving to Corvallis, Oregon in 1950. So he just says, it struck me that I still remember where it was, is that when the thing dawns on you, it's kind of like a landmark, so to speak. Okay, we'll pick up from there. The same thing was true when I first got the idea what electric current was. I can remember that. I was around 10th Street in Portland, crossing the street just by the library. It's kind of striking situation you see when you get an idea that's immediately clear, a crucial idea. The idea, of course, in the electricity matter was that electric current is just space moving through matter. It's a silly idea when you take a look at it, but that's the way it works out. Questioner, it seems like such a simple concept, actually. Larson, yes, it's a simple thing. No matter how silly it sounds, it's obviously correct. If you've been working on the thing and you can see immediately when you get this idea that everything falls into place again. Question, was that a few years after your realization of the reciprocal relation? Larson, well, I can't remember when that was. That must have been a little while after that, because I didn't attempt to get into any work with electric or magnetic matters until quite a way down the line. As far as magnetism is concerned, once you get the idea as to what the electrical situation is, it's obvious that the magnetic phenomena are the two-dimensional analogs of the electrical phenomena. Question. That was the point, I suppose, at which you decided to publish your findings. Do you remember when that was? Larson. That was about the middle of the 1950s, when I came to the conclusion that it ought to be published. I sized up the situation and decided that I had about 5 years of steady work ahead of me before I'd have enough of the loose ends tied up to be able to publish anything. So I was toying around with the idea of getting connected with a university to get access to the university facilities, as well as the time that I didn't have while earning a living doing something else. A friend of mine happened to be the dean of engineering at Oregon State then, so I talked to him about it and let him read what I had ready thus far to give him an idea about what I had in mind for completing it. At that time, he was on the committee of the National Science Foundation, one of the committees that picks out the projects to be funded. So the idea that he came up with was that he would arrange with the National Science Foundation to get a grant to take care of expenses, and then he would put me on the engineering department payroll along with a proposition of teaching half-time so that I could leave the other half-time to work on my research. It seemed like a very good proposition, but there was one catch in it. It had to be approved by the School of Science, and they turned thumbs down on us, so that fizzled out. Now, as it happened, it really didn't make any difference, because while I thought then that I had 5 years of work ahead of me, in only about 6 months, all of these loose ends came together, and I got to the position where I expected to be after 5 years of steady work. It just turned out that there were a couple of items that I hadn't seen clearly enough before, and once I got them, it was just like when a chemical solution turns into a solid at a certain point, all of a sudden. So then that then put me in a position where I was able to publish it. I spent a lot of time looking for a publisher. Question: you did try to find a commercial publisher? Larson: oh yes, but I didn't get very far with that. It came back just as fast as I sent it out. It even seemed to me as if I got it back before I sent it out. Anyway, I tried. So then, in the course of trying to get it published, I read all the things I could get a hold of about this publishing business. Of course, there are these outfits that will publish on a subsidy basis. But the people who write the books of advice about publishing tell you that that's not a very good deal, that you can do the same thing yourself a lot cheaper and come out just as well. So I decided I would publish it myself, which I did. Only I didn't have the finances to publish the whole thing. So I only published about 50% in the structure of the physical universe. I know that you list those sections you left out at the end of the book, but I didn't realize it was that much, says the questioner. Larson: it was at least half, if not more. What I had in mind then was that if I got anywhere with it, we would then publish the other half. But by the time we got far enough along to justify doing anything else, it was many, many years later and the situation had changed. So I don't want to go back and publish something that's that old, and that doesn't have the benefit of the new light on the subject that has developed in the meantime. Question: what happened when you published the book in 1959? Was it advertised? Was it reviewed? Larson: I sent out review copies on a pretty good scale, and all I got in the way of reviews was a couple of foreign notices. I did get a couple of reviews of The Case Against the Nuclear Atom, another one of his books, including the one by Isaac Asimov. But aside from that book, which really had nothing to do with the theory, there was no attention in this country. Question: were you contacted by scientists in those early years? Larson: not by established people. The attention I got was mostly from the same kind of people that we have now in the organization, and from students. I had quite a bit of correspondence with students, and initially most of the lectures I gave were sponsored by some group of students in one place or another, usually over the opposition of the faculty. Question: did you try other ways of reaching the scientists? Answer: the original publication of the work through my first book didn't get very far by itself. Something obviously had to be done to stir up interest, and what I decided to do was to write the series of articles on the liquid state of matter. That was one of the parts that didn't get into the book. And then send out an offer to selected scientists all over the world. I offered not only to send them the papers, but to send them a complimentary copy of the book. About 5% of them accepted that. So over a period of several years, I sent out these papers as I wrote them and developed apparently a constituency of people who at least had one ear open. It would be well to get the view of that project from some of those who received them. For example, a group of young scientists at Queen Mary College in England, electrical engineers, most of them, had a good deal to do with the direction which the development of the theory took. Question: I had no idea that there was a group there. Larson: that was in the rather early days of my effort to promote the thing. One of the professors there got a hold of the book and the liquid state papers. Something about it impressed him, and he talked to his students about it. Evidently, they were a group of more adventurous spirits than the ordinary class, so I had quite a bit of correspondence with them, and they are actually responsible for my undertaking to write more books after the first one. Really? Larson: what happened was that in the course of this correspondence, they had asked for certain things to be written. So I wrote something or other along the lines that they wanted. See his article called "Just How Much Do We Really Know?" And then it occurred to me that I might just as well expand that. That's how the case against the nuclear atom originated. I see. Larson: that was the origin of my idea of going on and writing more books about the subject. Otherwise, I might just have dropped it at the original point. Question: I can't believe you would have been able to drop it at that point. But why did you choose to send the liquid state papers to the scientists? Was the evidence more convincing there than in other places? Larson: there is no way you can verify a general proposition specifically, and the early work that I did was almost entirely confined to these basic propositions. And I figured then that there wasn't much use in trying to do anything more with the general principles. I covered them in the book, but I wanted my correspondents to know that those general principles could be carried down to specific items that could be tested. So I had to pick out one of the things that I had studied, and it looked to me as if the liquid state had more information than anything else at that time. So that's why I picked that. Question: is the liquid state easier to deal with than the solid state? Does it have fewer variables, maybe? Larson: well, in a way, yes, because it's more regular. In the solid, you go into so many variations. Take iron, for instance. You can't say what the density of iron is because you got to indicate the conditions under which you're measuring it. Not only that, but you're influenced by the history of the thing. Question: the stresses, for instance. Larson: the density of iron depends on what you've done to it in the past. Under the same conditions, it will have a different density if you've put it through certain processes. Not that the substance itself has changed any, but the way that the molecules interact changes. You don't have that in the liquid. The density under certain temperature and pressure is always the same. Question: so you can make predictions more easily. Larson: you can calculate definitely. As I've mentioned in my books, you can't calculate a specific interatomic distance for iron. You can never say the interatomic distance of iron is in the absence of thermal expansion and pressure is so and so. You've got to say the possible interatomic distances are such and such. Question, you can't be as precise with the solid. Larson, oh, you can be precise, but it's now going to be a series of values rather than a single value. It's a multi-valued proposition. But in the liquid state, you have a single value for a given property under given conditions. And then I found some things that I thought would be of interest to the people I was addressing. I am not so sure they were in retrospect. For instance, I found that there is a fourth state of matter. You mean the condensed gas state? Larson, yes, and I think that's an important point. You can observe it in the stars. It accounts for the surface of the sun. If it were just a gas, it would be diffuse. Larson, it would be just a cloud that gradually thins out. Question, one tends to think of the outer layers of the sun as behaving almost as a liquid because they're under immense gravitational pressures. Larson, well, they follow the liquid relationships in some respects, but of course it doesn't meet the usual definition of a liquid. Okay, we're going to stop right there. I do want to point out that the states of matter are very, very important in Larson's system. They apply in many different ways. And when they say that the fourth state of matter is the condensed gas state, in a different interview, he talks with KVK Nehru, and he talks about how the vapor state is another state of matter, liquid, solid, liquid, gas, but also vapor. And I would say that the condensed gas state is more like a fifth state of matter, and that is, it's more of an outlier, and that the vapor state is actually, within the same line of, I think Larson is basically attempting to say that they're the same, liquid and vapor. Okay, we'll leave it there, and we will talk tomorrow. Have a great day. Thanks for tuning in.